Is your mind a universe of its own? Do you often find yourself lost in thought, pondering the big questions about existence, gravity, and the very fabric of reality? If so, you're not alone. Today we're going to unravel one of the most mind-bending theories ever conceived. It's called string theory, and it's one that connects the smallest particles to the largest mysteries of the cosmos. So let's dive into the information about what the universe might be made of, what we can't see, and what it all means to you and me. Part 1. The problem with everything. For centuries, science and philosophy have been on a quest to find the ultimate building blocks of the universe. What is everything made of? We used to think it was atoms, then protons, neutrons and electrons. Then things got a lot weirder with quarks and other subatomic particles. But here's the catch. The more we zoomed in, the messier things became. The laws of physics that work beautifully on a grand scale, like with planets and galaxies, completely fall apart when you try to apply them to the tiny quantum world. It's like trying to use a map of a continent to navigate the intricate streets of a single city. They just don't fit together well. This is the fundamental problem that has stumped some of the brightest minds for decades. We have two powerful but incompatible theories: Einstein's general relativity, which describes gravity and the large-scale structure of the universe, and quantum mechanics, which governs the bizarre and unpredictable behaviour of particles at the smallest scales. These two theories are like rival siblings who refuse to talk to each other. They each do their job perfectly in their own domain, but they can't seem to agree on a universal language. According to physicist Brian Greene, as they are currently formulated, general relativity and quantum mechanics cannot both be right. Physicists have been searching for a unified theory, a theory of everything that can bridge this great divide. Part 2. String theory, a symphony of vibrating strings. This is where string theory enters the stage, and it's one of the most elegant and ambitious ideas ever proposed. Physicist Michio Kaku stated, "In string theory, all particles are vibrations on a tiny rubber band. Physics is the harmonies on the string. Chemistry is the melodies we play on vibrating strings. The universe is a symphony of strings, and the mind of God is cosmic music resonating in 11-dimensional hyperspace." The basic premise is simple yet revolutionary. What if all the tiny point-like particles we've discovered, including electrons, quarks, and everything else, aren't points at all? What if they're actually tiny, one-dimensional vibrating strings? Think of a violin string. When you pluck it, it vibrates at different frequencies, producing different musical notes. In string theory, the universe is a grand cosmic orchestra, and these tiny strings are the instruments. Each of the distinct ways a string can vibrate corresponds to a different particle. A certain vibration might create an electron, another might create a quark, and yet another might create a photon, the particle of light. This simple idea has some profound implications. By seeing everything as different notes played by the same fundamental string, string theory promises to unite all of the known forces of nature, such as gravity, electromagnetism, and the strong and weak nuclear forces under one elegant framework. It's like finding a single sheet of music that explains every instrument in the orchestra. But there's a huge catch, and it's a doozy. For string theory to work mathematically, it requires the universe to have more than the 4 dimensions we know: length, width, height, and time. Most versions of the theory suggest that there are at least 10 or 11 dimensions. We don't see them because they are curled up and incredibly small, hidden from our view. Imagine a tightrope walker. From far away, the rope looks like a one-dimensional line, but up close you can see that it has a second dimension, which is the tiny, curled-up space where the walker's feet can move. String theory suggests our universe has similar hidden dimensions, and the way they are curled up determines the laws of physics we observe. Part 3. The universe's silent partners, dark matter and dark energy. Here's what keeps physicists awake at night, and probably you too if you've ever really thought about it. We can only see about 5% of our universe. The other 95% is invisible, mysterious, and completely changes how everything works. Scientists call this hidden reality dark matter and dark energy, but those names are just fancy ways of saying we have no idea what this stuff is. Dark matter makes up about 27% of the universe. You can't see it, touch it, smell it, taste it, hear it, or detect it directly, but it's there, holding galaxies together like an invisible glue. Without it, stars would fly apart and galaxies would never have formed. Dark energy is even weirder, as it makes up 68% of everything, and it's pushing the universe apart, making it expand faster and faster. We know dark energy and dark matter are out there because we can see their effects, but we can't see them directly. Think of a gust of wind on a quiet day. You can't see the wind itself, but you can see the leaves rustling and the trees swaying. That's a good analogy for how we know about dark matter and dark energy. Dark matter holds galaxies together. We can tell it's there because galaxies spin much faster than they should, based on the stars and gas we can see. Without the extra gravity from dark matter, galaxies would literally fly apart. So, what does string theory say about this? Well, string theory proposes a whole menagerie of new exotic particles, such as superpartners, branes, and cosmic strings. It's entirely possible that some of these new particles could be what we call dark matter. In this sense, string theory doesn't just explain the known world, it offers a whole new set of possibilities for what the invisible world could be made of. Here is another thought on how string theory addresses dark matter. This idea is that dark matter consists of particles that are hidden in larger, unseen extra dimensions. These particles would interact primarily through gravity, making them undetectable by conventional means. In this model, the gravitational force might behave differently on very small scales due to these extra dimensions. This could manifest as a dark dimension that influences gravity in our observable universe, providing a potential explanation for the presence of dark matter. Then there's dark energy, the mysterious force that is causing the expansion of the universe to speed up. It's the universe's ultimate accelerator, and we have no idea what it is. String theory's extra dimensions might hold a key here. The behaviour of these tiny, curled-up dimensions could create a subtle pressure that acts like dark energy, pushing the universe apart. So while string theory doesn't give us a final answer, it provides a compelling framework where the pieces of this cosmic puzzle might actually fit together. If there are 10 or 11 dimensions, then dark energy could arise from properties of these extra dimensions, such as the curvature of a dual space in certain string theory models. Another concept related to string theory is the idea of brane worlds. Our universe might be a brane, short for membrane, existing within a higher dimensional space. Interactions between our universe and other parallel universes could produce a repulsive force, causing the accelerated expansion of space attributed to dark energy. String theory models aim to provide a natural explanation for the value of the cosmological constant, which is related to dark energy, rather than requiring it to be a separately added constant. Part 4. So what is superstring theory? The super is the key. It's short for supersymmetry, and it's a huge step up from the original string theory. In our universe, we have two basic families of particles. Bosons, which are the force carriers like photons, light particles, and fermions, which are the matter particles like electrons and quarks that make up you and me. The problem with early versions of string theory was that it could only describe the bosons. It was missing half the picture. Superstring theory fixed this by adding a new layer. It proposes that every boson has a superpartner fermion, and every fermion has a superpartner boson. These superpartners haven't been discovered yet, but the mathematical framework of supersymmetry allows the theory to describe all known particles and forces. This is more than just a clever fix. It's what makes the theory powerful and appealing. The combination of strings and supersymmetry naturally includes a particle that acts exactly like a graviton, the theoretical particle that carries the force of gravity. This is a monumental idea because it means that superstring theory offers a way to finally marry the two great rivals of modern physics: general relativity, which handles gravity and the large-scale universe, and quantum mechanics, which describes the tiny world of particles. For a long time, these two were like oil and water, and now, for the first time, we have a single, unified idea that could bring them together. It's not just a theory of everything, it's a theory in which, finally, everything makes sense. Part 5. Ancient wisdom meets modern puzzles. Now for the philosophical part. How would the great thinkers of the past react to all this? The fascinating thing is that philosophers have been wrestling with these ideas for thousands of years, long before anyone dreamed of string theory. Democritus of ancient Greece proposed that everything was made of tiny, indivisible particles he called atoms. He was remarkably close to modern thinking, suggesting that reality has hidden layers we can't directly perceive. Plato would have likely found string theory fascinating. He believed that the physical world was just a shadow of a perfect ideal world of forms. A theory that suggests a deeper, more fundamental reality, a reality of vibrating strings and hidden dimensions, would resonate deeply with his ideas. The universe we see would be like the shadows on the wall of his famous allegory of the cave, with string theory giving us a glimpse of the true underlying reality. Aristotle, on the other hand, would be more skeptical. He was an empiricist and he believed in observing the world as it is. Since string theory's core ideas, like its extra dimensions and tiny strings, are currently impossible to prove with experiments, he would see it as a beautiful mathematical idea, but not yet a part of true science. He might call it a kind of metaphysical speculation, waiting for a chance to be put to the test. Even more intriguing, however, ancient Indian philosophers in the Vedantic tradition talked about reality having multiple layers, or koshas. They believe the physical world we experience is just the outermost shell of a much deeper, multidimensional reality. Modern string theory echoes these ancient insights with striking similarity. Modern philosophers, especially those who think about the nature of science and reality, are caught in a similar debate. Is a theory that cannot be proven by experiments still a valid scientific theory? Or is it more like a piece of art or a philosophical argument? Karl Popper, who developed the idea that scientific theories must be testable to be meaningful, would probably be skeptical. String theory makes predictions about energy scales so high that we might never be able to test them directly with experiments. But other philosophers argue that string theory's beauty and mathematical consistency might be pointing toward truth in ways that go beyond simple experimental verification. The philosopher of physics, David Albert, suggests that sometimes the deep mathematical structures of a theory can guide us toward understanding even when direct testing is impossible. Thomas Kuhn, who studied how scientific revolutions happen, might say that string theory represents exactly the kind of paradigm shift that changes how we see everything. It's not just proposing new facts. It's suggesting that our entire framework for understanding reality needs to expand. Here's a thought. If you get to the end of your life and you don't have all of the answers about the universe, what then? This is where your deep, introspective mind comes in. This is a question not just for a lab, but for your own inner world. The idea of hidden dimensions of a universe as a symphony invites us to look at the world differently. It's a call to push beyond the obvious and to find beauty in the unseen. Part 6. A quiet revolution. So what does all of this mean for you? You, the person who spends their time thinking deeply about the world, seeking patterns and finding comfort in the logical unfolding of complex ideas. String theory, whether it turns out to be right or wrong or part of a larger puzzle, is a monument to human curiosity. It's a testament to the idea that even when we hit a wall, we don't give up. We invent new ways of seeing, new ways of understanding, and new ways of connecting the dots. String theory reminds us that the biggest mysteries of life and reality are often in hiding. It's a reminder that the universe might be far stranger and more beautiful than we could ever imagine. Just like the quiet mind that finds a whole universe of thought within itself, string theory suggests that our own universe is a place of incredible, hidden complexity. And perhaps the answers we seek aren't just out there in the cosmos, but also within the quiet depths of our own minds.